So section 2.1 starts with ionic compounds. So charged particles are called ions. For example, the sodium ion here, Na+. This tells us we have a sodium atom that has lost an electron. It's become positively charged. Compounds that contain ions are called ionic compounds. Remember that opposite charges attract, so this helps us put ionic compounds together. And remember that identical charges repel. We don't often see two identically charged species in the same compound. So metals, remember that metals are primarily in the main group. The transition metals here. There's the main group metals here. And some of these under the staircase are also metals. So the majority of the periodic table is composed of metals. They will often lose electrons and give that electron or electrons to a non-metal atom, and then the metals become positively charged. They're called cations, and they have fewer electrons than protons. So for example, neutral iron has 26 protons and electrons according to its atomic number. If that iron loses 2 electrons to a non-metal atom, it then will have 24 electrons to balance with 26 protons. And so the overall charge on here, we have 2 additional protons compared to the electrons. So the iron is a 2+ charge. It has a 2+ charge. On the other hand, nonmetals can often gain electrons from metal atoms and they become negatively charged. Those are called anions. So a negatively charged ion is called an anion. And anions have more electrons than protons because they have a negative charge. For example, oxygen starts off with 8 electrons and 8 protons. Again, we see oxygen right here, element number 8. Neutral oxygen has 8 electrons and 8 protons. If it were to gain some electrons, say 2, to have 10 electrons and 8 protons, now the oxygen would have a 2- charge. It has 2 more electrons than it has protons. And these charges will always be as integer units. We'll never have a 1.5 charge on an ion. So forces between the cations and anions are called electrostatic attractions, and these are what are responsible for holding ionic compounds together, electrostatic attractions. And ionic compounds are also called salts. So table salt, NaCl, is an example of an ionic compound. So when we look at the symbol for an ion, that indicates its charge. As we saw before, we saw Fe2+, iron 2+, and we saw O2-, oxygen 2-. So other examples, sodium with a 1+ here. We don't write the 1, that's understood. Iron 3+, here we include the 3 to indicate it has 3 positive charges. Again, we saw O2-. And here's iodine with a 1- charge. The values following the atomic symbols indicate the magnitude, 3, and the type of charge, plus, per ion. Remember that valence electrons are the outermost electrons in an element. Those are the ones that are lost by the metal atoms. This is called ionization. Again, that forms a cation because we've lost negative charge. We're left with extra positive charge. Now, nonmetals, when they gain electrons, they gain valence electrons. Again, the outermost electrons are the ones that are built up in a nonmetal when it gains electrons. And that will form an anion as there's excess negative charge now. And so when metal atoms lose electrons or nonmetal atoms gain electrons, the goal for both is to have a filled valence shell. Typically that means 8 electrons in the valence shell. So that helps us then decide how many electrons an atom will gain or lose. So for example, if we start with calcium and the question asks us, what type of ion does calcium form? Well, we look at calcium. It's in group 2A. It's right here. It is element number 20. And we know that because it's in group 2A, it has 2 valence electrons. And so that's going to tell us that it will lose both of those valence electrons to become calcium 2+. It's lost 2 electrons, so it gains 2 positive charges. Transition metals, however, again, those are the ones present in this block here, can vary in the amount of electrons that they lose. So, for example, iron could be iron 2+, or it could be iron 3+. So here's, again, an example from group 1A. Here's sodium. It's element number 11, so it has 11 protons and 11 electrons. Remember, the n equals 1 shell holds 2 electrons. N equals 2 can hold 8. and we put the 11th electron in the n equals 3 shell. It's in group 1, so it loses 1 electron to become ionized. We lose that electron. We go to picture B. That has a filled valence shell in n equals 2. Now this is the valence shell, right? It's the outermost shell. Whereas the unionized sodium, the outermost shell was n equals 3 with 1 electron. If we lose that electron, the outermost shell becomes n equals 2. We have a filled valence shell. It's a sodium ion with 1 plus charge because we still have 11 protons, but now we only have 10 electrons to balance that. Notice that the sodium ion now has the same electron configuration as neon does. And that's the goal. The goal is to lose or gain electrons so that they can become have an equivalent electron configuration to the nearest noble gas. If we look at the periodic table, here's sodium. The nearest noble gas is not argon, which is 8 spaces away. If we go backwards 1 from 11 to 10, it's neon. So sodium will lose 1 electron to become like neon in its electron configuration. And all group 1A elements will lose 1 electron. Lithium, sodium, potassium, rubidium, cesium, and francium. All of these will lose 1 electron to go backwards to the nearest noble gas. If we look at group 2A elements, again they have 2 valence electrons, so they will prefer to lose 2 valence electrons. Here's magnesium. 2 valence electrons in the n equals 3 shell, loses both of those to become of this electron configuration, which also is like the electron configuration of neon. So starts off with 12 protons, 12 electrons. Now magnesium ion has 12 protons and 10 electrons, so it is a 2 plus ion. And so here we can look at a couple of the ionic forms of the micronutrients. Notice in the transition metals here, they have sometimes several different ionic forms, but however in group 1A, they all form 1 plus cations. Group 2A, they all form 2 plus cations. Here are the nonmetals forming anions. We haven't quite discussed them yet, but we can see that fluorine, chlorine, bromine, iodine all will gain 1 electron to become a 1 minus ion, and that puts them to the nearest noble gas configuration. They gain 1 electron to become like their neighbor, the noble gas. So nonmetals will gain electrons to achieve a full valence shell. So we'll start with fluorine. Has a total of 9 protons and 9 electrons, 2 of which reside in the n equals 1. 7 reside in n equals 2. So in order to achieve a noble gas configuration like neon, fluorine needs to gain 1 more electron. So it gains an electron. It has a full valence shell, 8 in the n equals 2 shell. Looks just like neon. And that is true for any element in group 7A. So all of the halogens will prefer to gain 1 electron. And this is called the octet rule. The octet rule because typically a valence shell consists of 8 electrons, or a full valence shell has 8 electrons. So sodium had 1 electron, it lost it, so its valence shell is now the n equals 2 subshell, and that has a full valence shell just like neon. Fluorine started off with 7 valence electrons. It gained 1 more to become fluoride with 1 minus. That has a full valence shell like neon. So the gain or loss of valence electrons to produce 8 valence electrons. Filled valence shell is again equivalent to the noble gas configuration. And of course group 8 elements here, the noble gases, do not gain or lose electrons because they already have the filled valence shell. They don't need to gain 1 or lose a couple to achieve that filled valence orbital, or filled valence shell, like we see here with neon. So how do we name these ions? So metal ions are named for the parent element. Sometimes we follow by the term ion. So Na is sodium, Na plus is called the sodium ion, or sometimes just sodium. And each of these, sodium versus the sodium ion, has different properties. So it's important to be able to differentiate between them. Nonmetal ions use the parent name with the syllable IDE as a suffix. So fluorine, neutral fluorine, starts off as just F. We give it 1 electron, it becomes F minus, it's called the fluoride ion. Oxygen turns into O2 minus, called the oxide ion. And of course, each of these has different properties too, oxygen versus oxide. So let's look at some practice problems. Let's write the symbol for the ions formed from the following elements: selenium, arsenic, magnesium, and lithium. So the first thing to do is to find selenium on the periodic table. We can start by looking for Se, because that is the elemental symbol for selenium, and it resides right in the middle of the main group elements, selenium. It's in group 6A. So the closest noble gas to selenium is two more further on down the line, Kr or krypton. So in order to achieve the octet, or the filled valence shell, selenium wants to gain 2 electrons to become like krypton. So we can write the elemental symbol Se, and remember it gained 2 electrons to become like krypton, so we go 2 minus, because electrons are negatively charged. If we add electrons, we become negatively charged. So arsenic is the next element. Ar is, actually it's not Ar. It is right here, As, arsenic. It's element number 33. And as we see, just like selenium, the closest noble gas is krypton. So if we count 1, 2, 3, we need to gain 3 electrons to become like krypton. So we're going to write arsenic, again, As, 3 minus, to become like the noble gas krypton. Magnesium, we know that that is Mg. If we look at the periodic table, most of us, I think, will remember that magnesium is in group 2A. So its nearest noble gas is not argon. It's 2 behind it. 1, 2 to get to neon. So magnesium will lose 2 electrons to become like neon. And so that makes it 2 plus. Right, we've lost 2 negatively charged electrons, leaving behind an excess of protons. So magnesium 2 plus. And lithium, we'll find lithium element number 3. It's right here. It's in group 1. It needs to lose 1 electron to achieve the noble gas configuration of helium. So lithium simply gains 1 plus charge, Li plus. So let's consider these ions I minus, N3 minus, and Cr3 plus. Indicate the number of protons and electrons in each. So let's look at I minus. The number of protons in iodine, 53 protons, right, because the atomic number is 53. And since ions don't lose protons or gain protons, we still have 53 protons. And I'll just write a P there. And because it's a minus charge, we know that it has 1 additional electron compared to the number of protons. So it should have 54 electrons. And I'll abbreviate electrons E minus. That's the symbol I will use to abbreviate electrons. So now nitrogen 3 minus. Looking at nitrogen, that's element number 7, right here in group 5A. So element number 7, we know that it has 7 protons. Since it has 3 extra negative charges, it has to have 3 additional electrons. So it has 10 electrons. Chromium 3 plus. Let's look at chromium. That's a transition metal. It's in row 4. It's element number 24, chromium. And so, of course, it has to have 24 protons. 24 protons. Now it has 3 positive charges associated with it, meaning it has 3 more protons than it has electrons. So it should have only 21 electrons in order to become a cation. State whether the ion was formed from a metal or a non-metal. So iodine is way on the left of the periodic table. I'm sorry, the right side of the periodic table. That is a non-metal. And nitrogen is also a non-metal. It's located in the upper right. And as we just saw, chromium is a metal. It's located in the transition metal block of the periodic table. And then we're asked to explain why the charge on the ion is as indicated. Well, we just discussed that. The charge is negative in iodine's case because it's gained 1 electron. The charge is 3 negative in nitrogen's case because it has 3 more electrons than protons. And the charge is 3 plus in chromium's case because it has 3 fewer electrons than protons. Give a name for each ion. Well, with nonmetals and anions, we name them iodide. We take IDE as the suffix. Change iodine to iodide. Nitrogen changes to nitride. And chromium stays as chromium, and just to be sure, we'll label it as chromium ion.